Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his master's in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series in bioarchitecture. In the previous lecture, we have seen a two-way restraint slab which is having a condition of one long edges discontinuous. In this lecture, we are going to see the design of a restraint slab with 3 edges discontinuous and 1 long edge continuous. So, using this condition, how to design the two-way restraint slab using the moment coefficients which is given in IS 456-2000 in table 26. So, in the case of restraint slab, the 4 corners of the slabs are prevented from lifting, that is called as a restraint slab. So, in this design, we are having a problem of, that is, design a reinforced concrete slab for a room of size 4 meter by 5 meter. In the previous lecture, we have seen a square slab with the condition of one long edge discontinuous, but here we are going to see the design of 4 meter by 5 meter slab which is subjected to a live load of 2.5 kilonewton per meter square. 3 edges are discontinuous and 1 long edge continuous. And how to find out the bending moment coefficient from IS 456 from the table 26 for the design of this slab with a condition of 3 edges discontinuous, 1 long edge continuous. The load due to the floor finish is 1 kilonewton per meter square and the partition is 2 kilonewton per meter square. Use M20 and Fe 415 as materials. Now, this is a table, this is I have already told you that it is a table which has to be used for finding the bending moment coefficient for the two-way restraint slab, which all the conditions, that is interior panel, 1 short edge discontinuous, 1 long edge continuous, like that. They have given the various moment coefficients for the various conditions of the slab. Now, here in our case, the condition of the slab is 3 edges discontinuous, 1 long edge continuous. 3 edges discontinuous, 1 long edge continuous. That is the condition. 3 edges discontinuous, 1 long edge continuous. 3 edges discontinuous, 1 long edge continuous. So, we are going to use this moment coefficients for finding the bending moment. 3 edges discontinuous and 1 long edge continuous. So, here the clear dimension of the room is 4 meter by 5 meter, which is supported on walls. That is, we can assume that it is supported on wall and effective dimension of room is 4.23 meter by 5.23 meter. So, thickness of support is 230 mm, that is all. So, here Ly by Lx. So, this is Ly and this is Lx, that is 5.23 by 4.23, which is equal to 1.24, which is less than 2. It confirms it is two-way slab. Now, we need to first calculate the load acting on the slab. First step is load calculations. So, in the previous case, we have seen 1 long edge discontinuous, that is we have used this as the moment coefficient for design of the two-way restraint slab in the previous lecture. But in present lecture we are going to design the two-way restraint slab using the different edge condition, that is 3 edges discontinuous, 1 long edge continuous. Load calculations, first one is dead loads. So, first we are going to assume the thickness of the slab from the deflection criteria, that is L by D ratio is equal to 20. That is, here in the case of rectangular two-way slab, we are going to use the shorter direction for calculating the depth of the slab from the deflection criteria. So, D is equal to L by 20, which is equal to 4230 divided by 20, which is equal to 211.5 millimeter. So, overall depth of the slab is 211.5 plus 15 plus 10 by 2, that is equal to 221.5 millimeter. So, when you add, that is 231, sorry 231, 20 add 20, that is 231 millimeter. But I am going to keep, again as in the previous case, I am going to keep overall depth of as D is equal to 150 mm. Small d is 150 minus 15 minus 10 by 2, that is equal to 130 millimeter. I am going to find out the self height of the slab. Self height of the slab is 0.15 into 25, which is equal to 3.75 kilonewton per meter square. In addition to this, they have asked us to consider load due to the floor finish and the partition wall. Load due to floor finish, that is equal to 1.0 kilonewton per meter square, and due to partitions, that is 2.0 kilonewton per meter square. So, total dead load on slab is W d is equal to 5.75 kilonewton per meter square, and the live load on the slab is 2.5 kilonewton per meter square. Second one is live load on the slab, WL is 2.50 kilonewton per meter square. Next, total load on slab, W equal to WD plus WL, that is equal to 8.25 kilonewton per meter square. This one is 9.25 kilonewton per meter square. Next step, bending moment. Bending moment calculations from table 26. We are going to use table 26 of IS 456. So, the condition is 3 edges discontinuous and 1 long edge continuous. Ly by Lx ratio, here it is, that is we have calculated as 1.24. Now, alpha x, the bending moment coefficient in x direction, that is alpha x, that is first one negative moment coefficient. So, here this is the value in between, here it is 1.24 for 1.2 alpha x and 1.2 and 1.3. So, this is the value is in between 1.2 and 1.3. Alpha x for 1.2, that is negative moment coefficient is 0.071. This is negative moment coefficient, and positive moment coefficient, that is alpha x, that is 0.053, and for 1.3 it is 0.076, 0.057, and for alpha y, So, this is for alpha x, and for alpha y positive moment, negative moment coefficient, there is no negative moment coefficient, and there is a positive moment coefficient of 0.043. 0.043. So, we need to select the alpha x for the value of 0.24 by interpolating the values. Alpha x, negative moment alpha x, positive moment alpha x. So, negative moment alpha x, here it is 0.073 and positive moment coefficient is 0.0548, and alpha y, there is only one alpha y, that is 0.043, that is only the positive moment coefficient in the y direction. So, among these two we have to select the maximum moment coefficient, that is 0.073. So, maximum moment coefficient alpha x is equal to 0.073 and alpha y is 0.043, and m u x is equal to 1.5 into alpha x w L x square, m u y is equal to 1.5 into alpha x w L x square. So, that is equal to 1.5 into 0.073 into the total load acting on the section is here 9.25, L x square is 4.23 square, which is equal to, so 17.28 kilonewton meter. M u y, that is 1.5 in alpha y, 0.043 into 9.25 into 4.23 square, that is m u y, here it is 10.17 kilonewton meter. So, among these two bending moment, there is a maximum bending moment, that is m u x, which is used to calculate the effective depth of the slab. So, next one we are going to calculate effective depth of the slab. Effective depth of slab D. Consider 1 meter width of slab, and also consider a balanced section. In the case of balanced section, to find out effective depth of the slab, we are going to equate m u to, that is m u maximum to m u limit. That is m u maximum, here it is 17.28 into 10 to the power 6, which is equal to 0.138 f c k b d square. So, d is equal to square root of 17.28 into 10 to the power 6 divided by 0.138 into 20 into 1000. So, we are using M20 grade concrete. So, effective depth of the slab, here it is 79.13 millimeter, which is less than 130 millimeter, that is assumed value. Hence, it is safe against flexure. Now, we need to check the depth of the section again against the deflection after finding out the area of the reinforcement. So, then for up to that, I am going to keep the assumed value, that is 150 mm as the overall depth of the slab, and effective depth of the slab as 130 mm. Next step is area of reinforcement. So, first along shorter direction, that is for the bending moment m x. M u x is equal to 17.28 kilonewton meter. So, m u x is equal to 0.187 f I a s t into d minus 0.416 x. Since it is under reinforced section or singly reinforced section, I am using the respective expression for finding the area of reinforcement. So, 17.28 into 10 to the power 6, which is equal to 0.87 into Fi into AST into D is 130 minus 0.416 into XU, here it is 0.05 AST, that is XU which is normally found from the expression 0.87 Fi AST divided by 0.36 FCK B, that will be 0.05 AST. So, by solving this expression, I am going to get a quadratic equation, that is AST square minus 6249.87 AST plus 2.30 into 10 to the power 6, which is equal to 0. So, by solving this quadratic equation, I am going to select the minimum root, since it is under reinforced section, that is 393.25 millimeter square. So, and we can check this with the minimum spacing. So, normally it is very less than this AST required. So, here I am going to find out, I am going to use 8 mm diameter bar. Spacing of reinforcement, that is pi by 4 into 8 square into 1000, since we are designing the slab against 1 meter width. So, the spacing of reinforcement should also be found for 1 meter width of the slab. The spacing is 127.82 millimeter. I am going to check before finalizing the spacing of reinforcement. I am going to check with the this spacing with the maximum spacing as per IS 456. The maximum spacing should not exceed the least of the following, that is 3 into D, another one is 300 mm. So, 3 into 130, which is equal to 390 millimeter. The least value here it is 300, which is somewhat more than 127.82. So, A provide 8 mm diameter bar at 110 mm center to center. This is the reinforcement along shoulder direction. So, AST provided, here it is pi by 4 into 8 square into 1000 divided by 110, which is equal to 456.96 millimeter square. This is a AST I have provided along x direction. Now, along longer direction, here MUy is equal to 10.17 kilonewton meter. In the same way, by equating, that is MUy is equal to 0.87 Fi AST into D minus 0.416 XU. We have already found XU is equal to 0.05 AST. By substituting in this expression 10.17 into 10 to the power 6, which is equal to 0.87 into 4 and 5 into AST into 130 minus 0.416 into 0.05 AST. Now, by solving this equation, I am going to get a quadratic equation. So, by simplifying this expression, I got a quadratic expression of AST square minus 6249.87 AST plus 1.354 into 10 to the power 6 equal to 0. So, by solving this quadratic equation, I am getting the minimum root of, that is 224.72 as the AST required for the longer direction. So, by using 8 mm diameter bar, I am going to find out the spacing of reinforcement. The spacing of reinforcement is again pi by 4 into 8 square into 1000 divided by 224.72, that is equal to 223.68 millimeter. Now, here I am providing 8 mm diameter bar at 200 mm center to center along y direction. So, x direction is 8 mm diameter bar at 110 mm center to center, and along y direction it is 200 mm center to center. Now, finally, we need to check the depth of the slab against deflection. So, here L by D ratio is equal to 20, that has to be multiplied by, that has to be modified by multiplying with the modification factor. This has to be found from figure 4 of IS 456. So, these are all the curves which represents the stress in reinforcement. This graph which shows the modification factor versus percentage tension reinforcement. In order to find out the modification factor, we need to find out the percentage reinforcement. 100 AST provided divided by BD. For this, we need to substitute the reinforcement required for the maximum bending moment, that is 456.96 divided by 1000 into 130, that is equal to 0.35 percentage. And the stress which is developed in our reinforcement is 0.58 Fi AST required divided by AST provided, that is equal to 0.58 into 4 and 5 into AST provided is 456.96 and AST required is 393.25, that is equal to 207.14 Newton per millimeter square. Now, D is equal to L by 20 into modification factor. So, by using this to value the modification factor by referring figure 4, here it is 1.6. Now, L is 4230 divided by 20 into 1.6, that is equal to 129.06, which is less than 130 mm. This depth of section is safe against deflection, and also this depth is most economical. So, D is equal to 130 mm. Now, I am going to draw the cross section of the slab. So, along x direction, reinforcement is 8 mm diameter bar at 110 mm center to center. Along y direction, it is 8 mm diameter bar at 200 mm center to center. So, I am going to draw the cross section of the slab. This is the cross section of the slab which shows the reinforcement. So, here I am taking the cross section along x direction, that is 4.23 meter, along y direction it is 5.23 meter. So, here along x direction this is the straight bar and this will be the crank reinforcement. Alternate bar has to be cranked near the face of the support, that is 0.1 L from the face of the support. Here it is 0.1 L, that is it may be Lx if it is in the x direction, and if it is y direction it is Ly. So, here and another direction it is 8 mm at 200 mm center to center. So, both the reinforcements are main reinforcement since it is the two-way slab. So, here this is the reinforcement along shorter direction 8 mm at 110 mm center to center, and this reinforcement is 8 mm at 200 mm center to center. So, in the case of the plan view, so here this is the plan view. I will take the section here. So, this is the reinforcement along x direction, and this is the, if you take this as the wall, if you take the wall here, if you take the wall here, this is the reinforcement along y direction. That is all. So, this one is 8 mm at 110 mm center to center, and this one is 8 mm at 200 mm center to center. This is the arrangement of reinforcement or the detailing of reinforcement as per SP 34 for the two-way slab. So, here we have seen the restraint slab with the condition of 3 edges discontinuous and 1 long edge continuous, 3 edges discontinuous and 1 long edge continuous. This is the condition of this two-way slab. With this condition, we have found the bending moment coefficient from the table 26, and using the moment coefficients, we have found the bending moment at the respective places, and we have provided the reinforcement for the respective bending moment. Let us come to the end of this lecture. I summarize this lecture, that is, we have seen so far the design of two-way restraint slab. The slab, in this slab, the 3 edges are discontinuous and 1 long edge discontinuous. So, with these conditions, we have found the bending moment coefficient from the table 26 of IS 456, and we have found the bending moment for the respective bending coefficients, and we have also found the bending moment, we have found the effective depth of the slab for the maximum bending moment, and also we have designed the reinforcement required for the bending maximum bending moment along x as well as along y direction, and also we have seen the reinforcement detailing of the two-way restraint slab. So, in connection with this, there are certain questions. Design a two-way slab, two-way concrete floor slab for a room of size 3 meter by 5 meter when the corners of the slabs are prevented from lifting and subjected to a live load of 3 kN per meter square. The load due to partition wall is 2.5 kN per meter square and the floor finish is 0.6 kN per meter square. Use M20 and Fe 415 as material. The second problem, the design the reinforcement required for two-way simply supported slab for a room of size 6 meter by 6 meter clear. It is supported on 230 mm thick wall. The live load on the slab is 1.5 kN per meter square. In this case, 3 edges discontinuous, 1 short edge continuous. Consider other dead loads also and use M20 and Fe 415 as materials. So, from these two problems we can get much experience in the design of two-way restraint slab. In connection with this, the references are the plain and reinforced concrete code of practice, that is IS 456 2000, and IS 875 1987, which is the code of practice for design loads for buildings and structures, and SP 34 1987 handbook of concrete reinforcement and detailing. And in connection with the books, the reinforced concrete design written by S.N. Sinha and the reinforced concrete limit state design written by Ashok K. Jain. These two books are very important books in connection with the design of reinforced concrete slabs. Thank you very much.